Well, thanks for coming, everyone. This is a chance for me not to talk about the work we've done in the lab, but to try to put together work in the literature and epidemiological evidence that relates to some of the work that we do in the lab. So I was charged with, by ILSI, to look at the gaps in the knowledge we have about the role of sodium and potassium in blood pressure and in chronic disease. And here in my first slide, I have some examples of the top sources of sodium. So some of you, I think probably everybody in the room already knows, one of the top sources is bread. Even things that don't taste salty are giving us a lot of salt in a kind of an unregulated way unless we know where it comes from. And then top sources of potassium, another kind of favorite for me is that it's not just fruits and vegetables, but beans and coffee. So anyway, those are some of the things I learned along the way. I went to an NHLBI workshop in the beginning of December that focused on the question, why is hypertension incidence still going up when we're pouring all this money into hypertension research? And I see people in the room that are benefiting from that hypertension research. So amazingly, over between 1980 and 2013, there's been a 60% increase in the incidence of hypertension. So Barbara's already talked about the DRIs that just came out a couple of weeks ago, and they do address the point that potassium and sodium are interrelated. And I'm going to talk a little bit about that today, and how they're vital for maintaining body functions. And I've emphasized the last point, that the coexistence of essentiality with a relationship to adverse health effects, including chronic kidney disease, calls for a new approach to establishing intake recommendations for sodium and potassium. So I'll show you some of the clinical work that's been done over the last decade or so. And the limitation that I see, even though the DRI, this panel considered sodium and potassium together, they look at the recommendations for these separately. And I think that what we're going to do as a society eventually is start considering the ratios of intake. So this is a nice cover figure from our journal Physiology. And it shows some little organisms here coming up and going on to the dry land. So it all started with creatures crawling from the sea to dry land and bringing their fluid composition with them. And the first thing they've got to say to survive is they got to find some sodium chloride. So the kidneys, whether they're primitive or evolved, they evolved to reabsorb precious sodium chloride. They're just great at that. And to secrete plentiful potassium that's found in the food supply, or to conserve both during fasting. And we're all familiar with the cell membrane sodium pump, which keeps intracellular potassium high and extracellular fluid potassium low. The extracellular fluid sodium is very important for maintaining effective circulating volume, very important for life on dry land, and that's why we all crave sodium chloride. And we'll hear about some of that in later talks. So it's evolutionarily critical for survival. Now, intracellular fluid potassium is important for cell volume regulation, but also the membrane potential. If potassium falls or rises, it changes the membrane potential, it changes electrical excitability, and can give you a heart attack. So physiology optimizes extracellular fluid potassium over sodium. And that's something I'm just saying. You won't read that too much in textbooks, but I think the data agrees with that. The renin-angiotensin system evolved to help conserve sodium. It's activated when blood volume is low. When these organisms are drying out and they've got this low blood volume, it'll activate the renin-angiotensin system, which will produce angiotensin II and also produce aldosterone. And the net result is that it increases thirst to increase input, decreases output, and helps to maintain the cardiovascular volume. In addition, plasma potassium, if it gets too high, will stimulate aldosterone and promote potassium secretion mediated by sodium reabsorption. So this is a key system for animals and people eating low sodium, high potassium diets. So as primitive people before they figured out salt shakers. So we hear about the Yanomamo Brazilian natives, but there are still groups of people living on reservations in Ecuador in the Amazon basin that still live in a primitive way. And my son worked with these people over about 3 years making these fresh water tanks collection systems. And so they don't dress up like this all the time, but they're still people living on Earth that are eating just what's around them without salt shakers. And in the Yanomamo, the urinary sodium, which is a marker for intake, if we think about output equals intake, is very low compared to the U.S. average. Urinary potassium is very high compared to the U.S. average. And their plasma renin activity, that renin-angiotensin system, is high compared to what it is in the U.S. average. And we're always hammering on the renin-angiotensin system as a big problem, but actually in these people, they don't have blood pressure problem, and they have high renin-angiotensin, and their aldosterone is very high, indicative of the potassium they eat. We're familiar with this InterSalt graph from years ago, and it shows the Yanomamo have no increase in blood pressure with age, despite this really high renin-angiotensin system, whereas countries like the Bahamas and there's a few there, and I'll show you another example on the next slide. A very high sodium concentration in the diet is associated with an increase in blood pressure. So sodium, potassium, and blood pressure. So hypertension correlates with dietary, urinary sodium-potassium ratio better than with sodium alone. And that's been published a few times. And we also know that when people move from isolated, industrialized societies, both their dietary sodium-potassium ratio and their blood pressure increase. And there's some nice reviews there about that. In a recent review by Gritter and Horn, just published a couple of months ago in Hypertension, they review the role of dietary potassium and natriuresis, blood pressure reduction, cardiovascular protection, and renal protection. It's a great review. And they inserted this figure which looks at the systolic blood pressure increase with age. And Brazil, that must be the Yanomamo, they have very low sodium and high potassium intake and very little change in blood pressure with age. In Russia, where the sodium concentration is in the diet, sodium consumed is fourfold higher than it is in potassium, which isn't that far off from the United States. There's a very steep slope. And here we have Germany, which has the same intake of sodium, if not higher, but if they eat higher potassium, they have a lower slope increase in their blood pressure. So a couple of times it will come up, this J-shaped association between urinary sodium and cardiovascular events. And this was published by Mente and The Lancet in 2016. And they stratified the data looking at hazards ratio versus sodium intake in hypertensives and non-hypertensives, and they had plenty of subjects, more than 60,000. And most of the participants consumed between 4 and 6 grams of salt per day, and that's sort of the nadir here in both graphs. And if the sodium was raised further, blood pressure went up in the hypertensives, but not in the people who didn't have hypertension to start with. Blood pressure went up in both of them if the sodium was dropped around the recommended amount. So there are some considerations and caveats that were reported in editorials after this. One is that there's a very low number of people in this study who eat this recommended amount of sodium. It was based on only one morning urine, no consideration of K intake, and maybe the sodium intake was low in this population because they were sick, so they didn't stratify people according to their health. So this is also addressed in the DRI, and they criticize the use of single measures. They would like to see clinical studies include at least 2 24-hour urines, which is a tall order if you're looking at 120,000 people. So the same group, Mentis group, in a previous study, looked at the role of dietary potassium on blood pressure in the same population. And they found that for a given sodium intake, blood pressure was lower if the urinary, that is the dietary, sodium-potassium ratio is lower. So this is a little bit complicated, but it's useful once you get the hang of it. So they look at sodium, they stratify the population according to 3, 3.5, or 5 grams of sodium per day. This is down around the recommended amount. And then stratified it again according to potassium excretion. And you can see that raising potassium to greater than 2.5 grams per day helps whether you're eating a low or a high sodium diet. And I think that's a good kind of a take-home message. Raise your potassium, even if you're eating high sodium, it'll help. And it was mentioned by Barbara that the nutrition facts labels are used by they include the DSI information. And it's just this month that the nutrition facts labels now will include potassium. It's way down here, and it would be great if they moved it right under sodium and put it in bold, because then people could look at the label and in their heads calculate a sodium-potassium ratio. But we're moving in the right direction here. All right, so the question is, and I'll spend a little bit of time on biology, why is the incidence of hypertension and cardiovascular disease lower when you have high potassium, low sodium diet? And this is something that the Institute of Medicine doesn't necessarily agree with, so we'll look at the data for that. And higher with high sodium, low potassium Western diet. And the answer, I think, that the people in the field would agree on is that the body is doing a balancing act to maintain homeostasis of sodium and volume and potassium. And remember, potassium can give you a heart attack, and also osmolality. So it's doing this balancing act, but potassium has the high priority due to the critical importance of membrane potential. So there have been some recent discoveries in rodent models that indicate that sodium transport impacts potassium transport all along the renal nephron, from the proximal all the way to the distal part. And also, I'll spend a minute where I think I probably even took out the slide, looking at females versus males. So what happens if you eat a Western diet, an American diet, that's rather low in plasma potassium? Well, what happens, and I'll go back here if I can. Yeah, so along the nephron, there's the proximal nephron that does the heavy lifting for most of the sodium reabsorption. And then there's a small distal tubule region that has a set of transporters that are important for regulating salt and potassium. So if you eat a low potassium diet, it'll activate a potassium sensor in this distal convoluted tubular region and activate sodium reabsorption. So activate one of these powerful sodium transporters that's actually the target of thiazide diuretics. And that reduces, so you have low plasma potassium here, that'll reduce sodium delivery further down the tubule where sodium reabsorption stimulates potassium secretion. So increasing sodium reabsorption in the distal convoluted tubule helps you conserve potassium. And that's what this tubule is going to do. And this happens even during a high sodium diet. So if you eat low potassium and high sodium, low potassium plus high sodium, you'll activate these transporters, which you can see here on these Western blots looking at phosphorylated transporters, compared to high sodium with normal potassium. So dropping the potassium activates sodium reabsorption. So the takeaway message is low dietary potassium provokes sodium reabsorption. And so you're going to hold on to that sodium if you're eating low potassium, even if you're trying to follow the AHA guidelines. That's one of the take-home messages. So what about a high potassium diet? Something that, we could try that. Well, a high potassium diet facilitates sodium excretion. So a rise in plasma potassium, which we'll see after a potassium-rich meal, will inhibit sodium reabsorption via the sodium chloride cotransporter, deliver more sodium to the downstream sodium transporter, and facilitate potassium secretion. So normally high potassium, you eat a fruit salad, that will inhibit the sodium chloride cotransporter, activate transport via the epithelial sodium transport, and help you get rid of that high potassium diet, which is very important. It has the top priority. And you can see that here again with this phosphorylated sodium transporter, that it's very acutely dephosphorylated after eating a potassium-rich meal. And here you can see in this graph that if you look at electrolyte excretion, you not only excrete the potassium, but you also excrete more sodium, and that's because you've inhibited this transporter and also some transporters upstream. So is there a role of the proximal tubule where most of the sodium is reabsorbed? And the answer is yes. So a very nice 2018 paper from Young, Weinstein, Wong, and Palmer showed that eating a high potassium diet also reduces proximal tubule sodium reabsorption. So where most of the sodium is reabsorbed and most of the potassium is reabsorbed. So they say in their paper that under conditions of high potassium intake, decreased sodium reabsorption by the proximal tubule, which you can see here mediated by the sodium hydrogen exchanger, will lead to parallel decreases in proximal tubule potassium reabsorption, because that's mediated by a paracellular route. And you'll have a delivery of both sodium and potassium fluid downstream to the segments that will promote potassium secretion. So this is very nice evidence suggesting that now we can say that all along the nephron, raising dietary potassium reduces sodium reabsorption. And this was modeled by Ellen Weinstein. And he looked at the impact of the sodium hydrogen exchanger effects in this region, the loop of Henle effects, and the distal tubule. And it turns out that there's a major impact of potassium on reducing proximal tubule sodium hydrogen exchanger. This is proximal tubule alone, and this is reducing the transport all along the nephron. So that's an important contribution. So the takeaway message from the basic science is that potassium has a higher priority than sodium. High potassium diet reduces sodium reabsorption all along the nephron. It's like you're taking a diuretic your whole life. And during low potassium intake, sodium will be retained even if you're eating a really low sodium diet. It's going to be retained. And dietary strategies to raise K intake to suppress proximal and distal sodium reabsorption should be emphasized. So now let's go into a couple of epidemiology studies. I hope I have time for that. Yep, okay, we'll talk fast. So the potassium DRI said there is no sensitive biomarker for potassium requirements, and balanced studies didn't rigorously measure intake and all forms of losses in humans, limiting their ability to estimate potassium requirements. So they just concluded that potassium was okay, just eat what we eat, that it's apparently healthy groups of people. So those of us in the room here, we could think about some things like, well, maybe we should look at the urinary sodium-potassium ratio, and if the kidneys are desperately trying to retain potassium, probably you should eat more. And in fact, the DRI, the adequate intakes, the AIs, were decreased, as indicated in yellow here, from the previous version, and the previous version was based on Apple's DASH diet, but now they've reduced that to what the average is. So they say there's insufficient or low evidence for an effect of potassium intake on chronic kidney disease, but there's some evidence for blood pressure. And they really do think that the whole big issue is a lack of evidence for intake-response relationships. So I think most of us are familiar with the DASH diet, which actually started with non-hypertensive adults. People forget that that it was in non-hypertensive adults, they could show that increasing consumption of fruits, vegetables, and low-fat dairy would lower blood pressure, and you'd have a bigger reduction if you were eating higher sodium. And there's some kind of magic sauce in the DASH diet, because fruits and vegetables alone versus DASH didn't have such a remarkable effect. So there's something about the fiber, or I don't know what it is. There have been interventional studies that have shown positive impact of raising dietary potassium just by using 50/50 sodium chloride, lithium chloride salt. And one of the most dramatic effects is from this study in, can I keep going or should I stop?
Maybe a couple minutes.
Yeah, there's some time for questions, so you're just cutting in.
Okay,
Yeah.
so we'll have the questions later. So there is a remarkable effect of 40% reduction in cardiovascular disease mortality hazard ratio when Taiwanese veterans without kidney disease were fed 50/50 potassium chloride without their knowing it. So this was some evidence, and the ratio of sodium potassium in the study did not go to 1. It just went from 5 to 2.5, but it decreased mortality 40%. And this was followed up by a study in Tibet that had very similar results. There's a PREVENT study that prospectively looked at blood pressure in 5,000 people, and they showed that the people who secreted the most urinary potassium had a much lower risk of developing hypertension compared to the people who had less potassium in their urine. And I wanted to get to this one. This was just published this month in CJASN, the No CKD study. It's 1,800 patients with chronic kidney disease in Korea. And they studied them fairly rigorously and divided their urines into quartiles of potassium. So the patients that, we always think people with chronic kidney disease should limit their potassium, but it's the patients that had the lowest urinary potassium that had the highest incidence of problems, whereas the patients that had the highest consumption of potassium had much better survival. And so they concluded that low urinary potassium excretion is significantly associated with higher risks of adverse kidney outcomes. And this was significant regardless of age, diabetes status, or proteinuria. So that's worth looking at. And in defense of the spot urine, there was recently a study by Drunowski, who's very interested in potassium strategies. And he showed that, and this is a fairly recent paper in hypertension, and he showed that the spot urine sodium potassium ratio is a predictor not of just cardiovascular disease, but a very good predictor of stroke. And he makes the claim that this is easy to measure clinically and should be used more. So there are prospective studies that are being conducted. I'd like to just end on this. So Gritter and Horn assembled a number of questions, important questions to ask about potassium. And you're going to have to just read this list really fast. But they did get funding from the Netherlands and perhaps some institutes as well to do a study looking at, so this is ongoing, you can read about it in this paper, their design is published. So they're going to look at 133 people in each group, and they're going to supplement these CKD patients with potassium chloride or potassium citrate and follow their progression of their chronic kidney disease. So that's the kind of study that I think that the Institute of Medicine is looking for in order to really conclude that potassium has a benefit in chronic disease. And I'll just end there.
Great. Okay. Thank you.
Thank you. Sorry for going over.